Okay, good afternoon to all. So this is our second lecture of the course fluid mechanics. Okay, so in the previous lecture we have just discussed the importance of fluid mechanics, why we need to study it, and what are the different historical perspectives. So how different developments in the subject of fluid mechanics has taken place in the history. Okay, so now as we are studying about the topic fluid mechanics. So it is important at this moment to define first what is a fluid. So can any one of you answer what do you understand by the term fluid? Any one of you? Liquid. Then what about gas? Is it not a fluid? Molecules are closely packed in liquids. Okay. In fluids. Okay. Any other definition? Sorry? Something that can flow. Okay. Maybe bit close. Okay, so let's first define what is fluid. So what I will do, I will take this with the help of an example. Okay, so let's consider I have an object. So this is some object which is placed on some surface. So at the bottom I have some another surface. Okay, and this bottom surface is basically stationary. This is at rest. On the other hand, over this object I have also placed another surface. So here also I have another surface, and let's say to this surface I have applied a constant force of magnitude F. Okay. Now two important points we will make over here. First is the connection of intersection of this object and this surface is kind of rigid. So there is no relative motion in between the solid surface and this immediate layer of the object. Okay. Similarly, here also whenever this force is applied to this object, at this location also, if say this top surface is having some rightward motion because of the applied force, say if it is moving towards the right direction with some velocity, say u or du, in that case I can say that this top layer of the object will also move with the same. Okay, now let's differentiate this. If I use over here a solid object, so what will happen? If you simply take a solid, say this is the solid over here, if I apply force on this, then what will be happening? Depending upon the magnitude of this force, this solid over here will deform. Okay, so it means that say this is its original position before the application of the force. Once I applied the force, it may go to say this new state. Is this point clear? So in case of solid, you can see that say if this is angle d theta, then subjected to this force there will be some constant angular deformation. Is this point clear? On contrary, if in place of solid I take this object to be a fluid, then what will be happening? You have say water. Okay, so simple thing again similarly. So what I will be doing, say I have considered this one bottom plate which is stationary. I have considered one top plate which is subjected to a constant force F. Okay, and say this plate is moving in the rightward direction because of this force with some velocity d. Okay, now what will be happening if you place a fluid between? If you place a fluid between, so what will happen? Once again, we will assume that whatever is the velocity of this solid surface, that is same is the velocity of the immediate fluid layer which is just adjoining the solid surface. So why this happens, that we will discuss subsequently. Okay, but that particular condition is called as actually no slip condition. Okay, the meaning of no slip is that if this solid plate is stationary, then whatever the immediate layer of liquid which is just touching this solid surface, that will be also at the same velocity as that of the solid surface. Okay, so by considering this, what I can say that this bottom fluid layer will be at zero velocity, whereas the top fluid layer will be having velocity equal to that of the velocity of the plate. Okay, so if you do displace this, if you subject this to some force F, now you can see this F force is nothing but this is having some special characteristic. So typically when we have a surface, it is having two directions. One is parallel to the surface, one is normal to the surface. So over here when I am talking about this direction, this I am considering parallel to the surface. So this is nothing but a tangential direction. So this F I can call as nothing but my tangential force. So F, what I am referring specifically, I am calling F as nothing but my tangential force. So now when I will be subjecting this fluid element to this tangential force, so here I will be finding that because of the no slip condition, the bottommost layer will not move, but topmost layer will move with the velocity of the plate. Okay, so what I will be finding here, I will be having, say, this is some new location of the fluid at some time t1. Okay, but if I have constantly kept on applying the force, then it will not stop over here at some other time t2, which is greater than t1. My fluid will be somewhere over here. Then further it will keep on deforming. Okay, so what I can say that a substance which can resist the tangential force and give only a constant deformation, that is nothing but a solid. But a substance which continuously start deforming upon the application of the tangential force, that particular substance is called as a fluid. Is this point clear? Okay, so now you must be clear with the definition of the fluid. So the definition of the fluid is that, see, this is a solid surface. Here if I will be applying certain amount of force, so this solid surface is not continuously changing its shape with time. Depending upon the magnitude of the force, it may have certain deformation. Maybe at the moment that is also not visible, but say if we look from the microscopic perspective, there can be some deformation over this. Okay, but in place of this, if I consider, say, a column of fluid over here, and to that column of fluid if I apply the tangential force, then it will continuously keep on deforming. You can simply understand that when water is stored in a vessel, okay, so there are some sides of the vessel. If you just open one side of the vessel, then it starts flowing. Is this one clear? So what I am trying to say over here is that if any medium or any substance, if it is subjected to a tangential force, now whatever is the magnitude of the tangential force, even if it is very, very small, okay, upon the application of the tangential force, if it continuously start deforming, that substance we call as nothing but a fluid. Okay, so difference is simple. So now if you consider that the area which is in contact with this liquid or any object over here, say this area is A, so here also say the area is same A. So in this case, if I do calculate force per unit area, that will be nothing but my stress. Okay, so as I am considering the tangential force over here, so tangential force is typically also called as a shear force. Okay, so this shear force or tangential force per unit area will give us some quantity tau, which is called as shear stress. Is this point clear? Now corresponding to this shear stress, say I have this deformation over here as theta. So in case of solid, I will be finding that this deformation is nothing but a constant deformation. Once you apply the force, it will be deforming to certain angle and then it will remain at that point only. It will not continuously keep on deforming. So in this case, this deformation I can simply specify by a single angle value, and for solids, shear stress is directly proportional to this deformation. Okay, so this deformation is typically called as shear strain in case of solids. Is this point clear? On contrary, as I told you that corresponding to some time t1 in fluid, there will be some angle theta 1, for some time t2 angle can be theta 2. So this angle will keep on changing with the time. Okay, so instead of getting a constant strain, here angle is changing with time, so we will be having a rate of shear strain. Okay, so basically this angle is continuously changing with time, so I will be defining over here a parameter d theta by dt, which I can call as nothing but rate of shear strain. So in case of fluids, I can say that rate of shear strain tau shear stress is proportional to rate of shear strain d theta by dt. Is this point clear? So typically we have seen that any substance that is subjected to any amount of shear force, it can be very, very small. If it cannot resist the shear force, and upon the application of the shear force, it continuously keep on deforming, that particular substance we call as nothing but a fluid. On contrary, a substance which gives only a constant deformation, that is something which is called as a solid. Yes.
Is it different that for how much time the force is applied?
Yes. Even if it is for smaller duration, then also fluid will actually start continuously deforming.
But if it is for longer duration, the solid will want to.
So, if it is for longer duration, then also solid will not continuously keep on deforming. It will deform to certain time and then it will break. Once it has crossed it, first there will be elastic limit, then there will be, once it is crossing the elastic limit, then there will be plastic deformation, that if you remove the force, it will not come back to the original shape. And even if you keep on applying the load, once it has reached its critical limit of the load, then after that it will result in fracture. But it will not keep on continuously deforming with time. Is this point clear? So that is the difference between a solid and a fluid. Now, if we see, typically the principal phases in which a substance exists, these are nothing but solid, liquid and gas. Okay. So we have differentiated between the solid and the fluid. So typically liquids and gases almost behaves identical to the when they are subjected to the shear force. So that is why both the liquids and gases comes under the category of fluids. Okay, so fluid is nothing but, I can say that liquid plus gas jointly can be called as a fluid. Is this point clear? Okay, now let's understand that what is the difference between liquid and gas. Okay, so typically if you see from the molecular perspective, you will be finding that in case of solids, molecules are arranged in certain order and these are closely spaced. Okay, so this type of lattice arrangements you will be finding in case of solids. Okay, and of course your molecules are also very, very closely spaced in solids. So because of this close spacing of the molecules, there will be strong intermolecular forces or cohesive forces. On contrary, if you see, so this is the case of a solid. On contrary, if you see a liquid, in liquid also molecular spacing is almost identical to that of the solids. Okay, so say in liquid also I can say that molecules will be having almost the similar spacings, but the difference is that in case of solids, molecules are arranged in a particular lattice structure. On contrary, in case of liquids, molecules can be randomly oriented. Okay, is this point clear? So in case of solids, these are having definite locations. These will not move from these definite locations, but these can vibrate at their specific definite lattice positions. Okay. On contrary, in case of liquids, the molecules are not having any definite arrangement in which they are arranged, but still the intermolecular distances are almost comparable to that of solid. So that's why cohesive forces are quite moderate enough in case of liquids, but not very strong as that of the solid. Okay, but in comparison to gases, if I consider, then these liquids are also having strong cohesive forces. Is this point clear? On contrary, if you see a gas, so in case of a gas, you will be finding if one molecule is here, another is somewhere here. So these are randomly oriented, of course, and randomly moving here and there. Okay, so that is the reason that gases are having the least cohesive forces. Okay, so from molecular aspects, we have understood that what are the difference in terms of cohesive forces. But how at physical level we can understand that whether our substance, whether our fluid is a liquid or a gas. Okay, so that question comes now. So to differentiate this, what we can do is that if I put a liquid in a container, okay, so if say I take a container, and if in this container I put a liquid, say at atmospheric conditions, so I will be finding the liquid molecules will be over here. Okay, so this is under the atmospheric conditions and under the effect of gravitational force. So gravity is already there in our atmosphere and pressure is atmosphere. So I'll be finding that though molecules are here closely spaced, of course these molecules are having some sort of random motions also relative to each other. So what I can say is that a molecule, I can say that, say these group of molecules may be moving in this direction, then these group of molecules may be moving in some other direction, these group of molecules can be moving in some other direction. So group of molecules in liquids can have relative motion to each other. But while this relative motion is taking place, they are not changing their volume. So they are having some specified volume which is almost fixed. And another important thing is that when you pour a liquid under the gravitational field in a container, it creates, if the container walls, if it is not, container walls are not fully sealed, say from the top I don't have any wall in the container, so what it is doing, it is creating a free surface over here. So do you understand what is a free surface? So basically below this surface there is liquid, above this surface there will be atmospheric air, where air molecules will be at larger distance to each other. Okay, so if you pour a liquid in a container, it will be forming a free surface under the effect of gravitational force. On contrary, if you pour a gas in a container, let's pour now a gas in a container. So a container, once again identical to the previous case, this container is open from the top and it is open to atmosphere and it is also present in the gravitational field. Okay, so in this container if I see, I will be finding that if these are the air molecules, then they are not forming any free surface, rather these molecules outside are also having the equal spacing. So basically this creates the conditions inside the container equal to that of the atmospheric conditions. Okay, so under the effect of gravitational force, gravitational field, these specific type of fluids which are not creating any free surface, these we are calling as nothing but the gaseous fluids. Is this point clear? Okay, now any fluid, any liquid particularly, or any other fluid which is under the action of gravitational field, if it is at rest, so say I have a liquid over here, it can be say a water filled inside a container. Okay, so if I have water filled inside a container, So it is at the condition of rest. There is no motion of water inside the container. Of course, at the molecular level, molecules are moving, but at the bulk state, there is no motion in this container. Okay. So what I can say that this is the state of nothing but hydrostatic condition. Bulk means, so if I open this wall from the side, then whole liquid will start moving. Okay, for example, if you are having a pipe, so inside the pipe if liquid is flowing, so then a parcel of liquid from one location to other location is moving. Okay, on contrary, if you just close both the valves of the pipe, then what will be happening? Liquid is confined in the pipe, but it is not moving from one location to another location as a whole, okay, as a complete identity. So that is actually something which is the bulk motion, but obviously at the molecular level there will be some molecular motions. Okay, so what I am trying to say now is, when a water or any other liquid is actually poured in a container, when it is at rest, that situation we are calling it as hydrostatic condition. Now hydrostatic condition is something which is specifically the state when liquid is not having any shear stress. Okay, so corresponding to hydrostatic condition, liquid must have shear stress is equal to 0. Is this point clear? So shear stress of the liquid has to be 0. Then only it will be in a condition of hydrostatic. If there exists some shear stress, then obviously liquid has to move. Is this point clear? So how we can understand this better is that, let's consider I have a solid which is resting on some surface. So when it is resting on this surface, because of its own weight, it will be subjecting some pressure on the surface. Okay, so say if I simply take any, say, any control surface out of this solid, say A is my some control surface which I have taken out of this solid. So from the sides there is no interaction of this solid with any other substance. Okay, so from the side there is no restriction. So from these sides we will be having nothing but zero loading. Okay, so we will be having from the sides zero loading condition. So there is no force from the sides on this solid surface. On contrary, if you see from the bottom it is nothing but supporting its weight. So as it is supporting its weight, so say some pressure P is acting on from the bottom. So I am calling this as using the symbol P over here. Okay. So now before say explaining this, let me explain one more concept. If you have any arbitrary surface, and over this surface if you take a small control surface of area dA. Okay, so if this control surface of area dA is subjected to any force dF, this force can have two components. One is tangential to this area dA, so that is dF tangential component, and one component of the force can be normal to this surface dF. Okay, so if I take the ratio of normal component of the force per unit area, that is something which is called as sigma, and it is typically referred to as normal stress. On contrary, if I have tangential force dft by dA, then whatever the stress we are having, that we call as tau, which is nothing but our shear stress. Okay, so anything which is normal to the surface gives us, any force normal to the surface, that creates nothing but normal stress, and a force which is parallel to the surface, that creates a shear stress. Okay, now what I am trying to say over here is that in this situation, what just now I have shown previously, I have an element of solid which in one plane is subjected to zero force, There is no shear force over here, no normal force. But from the bottom surface, because this ground is giving some force which is just supporting the weight of this solid. So from the ground it is subjected to some, say, pressure P. Okay, so this pressure P is acting now in which direction? From this bottom surface it is in the normal direction. So I will be equating it equal to nothing but the which type of stress? Normal stress sigma. So I have called it as normal stress sigma, and I am writing it sigma equal to minus of P because it is acting inward. Okay. Now what if I do? If I plot a diagram for this solid such that this is my sigma axis, this is my tau axis. So sigma axis means normal stress axis, tau axis means shear stress axis. Okay. So on this surface you can see these left and right faces, these planes are nothing but subjected to zero normal stress and there is no shear stress as well. So if I locate this point, so this will be at this origin. Okay. But if I see the bottom plane is subjected to nothing but minus P sigma stress and there is no shear stress at the bottom. So this is at point minus P comma 0. Okay, so one plane is at this point and other plane is at this point. Okay, now if I form a circle which is passing through these 2 points, perhaps you have not studied continuum mechanics. So if you study continuum mechanics, there you will be knowing this concept in more details. Even this will be taught in strength of materials course. So this particular circle is something which is called as Mohr's circle. Okay, so what just now I have spoken, now mathematically I am trying to actually relate it. Okay, so what I am trying to say over here is that you can see a solid that in one plane it is at this point and in other plane it is at this point, and if we create a circle then it is called as a Mohr circle. Now if I just take any plane at certain angle theta over here, then what I can do with reference to this origin, if I take 2 theta angle over here, then whatever the point I am getting over here, this sigma and tau, these are nothing but the state of stress at this plane. So I can say at this plane sigma normal stress and tau shear stress is acting. Is this point clear? If you see on this physical plane, the 2 faces which we have considered, these were having how much angle? 90 degrees. But when I presented these on sigma and tau diagram, these are opposite to each other. So these are having angle of 180 degrees. So when we are representing these surfaces on sigma tau diagram, these are having angle 2 times of their physical angle. So that's why if any plane I have created at an angle theta, with reference line I have to create 2 theta angle over here to know the state of stress at that point. Okay. So if I know the state of stress at that point, so corresponding to this I am getting nothing but sigma comma tau, which clearly means that even when a solid is just resting on a surface, still it is having some shear stress at certain plane acting on it. Okay. Now just now in the previous slide I told you that when a liquid or any fluid is actually resting in a container, it will be in the state of zero shear stress. So how that will be in the state of zero shear stress, that I will explain further. Okay. So now let's consider that instead of solid we have a liquid or a gas, a fluid. So say a liquid water is resting. Okay. So now if for water I take any control surface of area, which is designated as A. So for this control surface you can see that the molecules which are just adjacent to the left wall of this container, these are subjected to pressure P from left. Aren't these? Because then only this is resting at this position. Otherwise, if I remove the wall, it will be flowing. So it means there is some resistance force which is acting on this from the container wall. So say from the container wall, P amount of force is acting. Now as it is as a bulk, it is in the stationary condition. So of course from the right side also same amount of force should act, then only it will be in the condition of rest. Now from bottom also there will be some pressure P. Of course from the top also there will be some pressure P. Considering that the size of the control volume is actually small, because as it will keep on increasing, the bottom pressure will be P plus delta P. It has to balance the weight, that we will study subsequently. So let's consider from other plane also. We have this pressure P which is acting on the surface. Okay. Now if I want to plot this on sigma and tau diagram, what will be happening? This is sigma, this is tau. So from left side I have value as minus P, normal stress is minus P and shear stress is 0 from left and right. So say this is the point over here, minus P comma 0. What is on the bottom plane? Same, minus P and 0. So what I am getting on sigma and tau diagram? Sigma and tau diagram, I am getting a Mohr circle which is nothing but a point. This Mohr circle is nothing but a point over here. So when I am having a point, it means it can only have a normal stress. It will not be having any shear stress. So a fluid which is in stationary condition, which is called as the hydrostatic condition, we can say that hydrostatic condition is defined for a fluid when it is subjected to the zero shear stress. So there will not be any shear stress in any plane of the fluid, because the primary definition of the fluid is that if it is subjected to any amount of shear stress, it will start flowing. Okay, so typically you can think of a bottle. If you have a bottle of water half filled, then you have some free surface. Now when you turn the bottle, it starts flowing unless a new free surface is created. Is this point clear? So for hydrostatic condition, the primary condition is that shear stress must be 0, because the characteristic of the fluid is that if you have given even infinitely small amount of shear force, then also it will start flowing. Okay, is this point clear?
But why is the vertical and horizontal direction? Why the horizontal and vertical direction?
Okay, same pressure. So typically whenever fluid is at rest, it applies the same amount of pressure. So we will subsequently, when we will go into the lectures, then you will understand this in more detail. Okay. Okay, so up to this point, is it clear? Or any confusion? Now there comes one important point. Yes. Sorry? Yes. Okay, so now another important question is that if you see, so that is maybe not that much fundamentally related, but say from practical perspective it is important. Okay, so when we talk about water, we say the gaseous phase of water as nothing but vapor. Okay, so typically we never say that water gas. What we call water vapor. On contrary, if you talk about air, you never say air vapor. You say air as a gas. Okay. So this is a simple practical reason behind that. The reason is that probably you will be further studying in your subject of thermodynamics properties of pure substances. So typically, if in properties of pure substances, if I represent the pressure and specific volume diagram, then this is the phase transition diagram, where this particular line is called as saturated liquid line. On the left of this line, phase remains in liquid phase. On the right side, it remains in vapor phase, and in between this line we have mixture of liquid plus vapor. Okay, and when these saturated liquid and saturated vapor lines meet, that particular point is called as critical point. Okay, is this point clear? So any gas, any gaseous medium which is having temperature very large in comparison to its critical point, that is typically referred to as a gas. Whereas any gaseous medium of any pure substance which is having temperature less than the temperature of its critical point, that is typically called as a vapor, because vapors, from vapor if you remove some amount of heat, it will immediately start condensing. So it is close to the saturation limit. Okay, if you remove, if you cool it, it will convert from gaseous state to the liquid state. So that is the practical reason behind this. So typically you can understand is that our atmospheric air is also having certain amount of water vapor in it. Okay, so all these water vapors, whenever we refer, we call water vapor or moisture sometimes we call. Okay, so you see during the cold winter days, whenever the night temperature goes down, then all these water vapors from the atmospheric air start condensing in the form of liquid droplets. Whereas the other gases such as carbon dioxide, nitrogen, oxygen, which are present in the air, these gases do not condense. So typically, because corresponding to the atmospheric pressure condition, whatever the critical temperature of these gases we are having, their critical temperature is in the range of minus say 60 degrees Celsius, minus 80 degrees Celsius, like that. So in comparison to that, our 25 degrees Celsius temperature is very large than the critical temperature. So even if we remove certain significant amount of heat, then also these gases are actually not changing from their gaseous phase to the liquid phase. So these are typically called as gas, whereas on contrary, the substance, though it is in the gaseous phase, but immediately it is starting condensing, it is called as a vapor. Okay, is this point clear? So that is the difference between the vapor and the gas. Now typically I think this might be discussed in the subject of thermodynamics as well. Whenever we analyze any fluid flow, so there are two approaches. One is we can analyze it from the macroscopic point of view, and second is we can analyze it from the microscopic point of view. So in macroscopic point of view, what we do basically, so let me write macroscopic versus microscopic approach. So in case of macroscopic approach, we are not interested in the individual molecular behavior. For example, this is a big room where all of you are sitting over here. In its surrounding, there are many air molecules. Even the number is too high. Okay, so many air molecules are there. But if you want to analyze this room, you don't want to understand that this air molecule is moving from here to there, how much pressure it is applying, and then sum up or average out the effect. But you are interested in, if you just put a pressure gauge over here, then whatever the average effect of that pressure is coming, we are interested in that. Then individual air molecules may have their different translational kinetic energies which are contributing to the temperature, but as a whole we are interested in what is the temperature in the room. So at a bulk level. So when we are looking, we are not looking into the molecular things, we are just looking the system as a whole at a bulk level, then we refer to the study as macroscopic study. On contrary, if you start looking into the individual molecular behaviors and then average out their effect to know the total value of parameter, that is something which is called as the microscopic approach. And microscopic approach is typically used in statistical mechanics or statistical thermodynamics, which probably if some of you from the engineering physics background are attending this course, you may have that as a core course. Okay. So important point is why we need not to go into the details of microscopic level for defining our average properties is that that is something which is the concept of continuum. So is the concept of continuum discussed in thermodynamics class? Not yet. Okay. So basically, we know that if I have a small container, in this container there will be number of molecules. So if say it is containing a gas, so there will be large number of molecules of that gas. And of course, these molecules are having random motion and some spaces between them. So these spaces between them are nothing but the void spaces. Okay, these are called as empty spaces, voids. Okay, so if you look this particular box and say if you consider in this box you are only having say, or let me give the example with the help of this room. Say this is a classroom. If I say in this classroom I have only 100 molecules, only 100 molecules are present. So what I have done, I have connected this first closed, completely sealed this classroom, and then I have used some vacuum pump to remove the air from this so that it is in a very rarefied state, okay, where very less number of air molecules are here. So if I have only 100 molecules present in this room, then what will be happening? I will be finding a large number of void spaces. Okay. On contrary, at present under the atmospheric pressure condition, I am pretty sure that this room, the size of the room like this, it will be having something around 10 to power 35, nearly equal to 10 to power 35 number of air molecules. So you can count the number. So with so many molecules, though molecules are moving here and there, these might have slight void spacing, but if you consider any control volume, okay, so say control volume is where I am standing, around me say 1 meter by 1 meter chamber I have created. So if I look into that 1 meter by 1 meter chamber at different time conditions, I will be finding almost same number of molecules present inside that chamber. Of course, there can be difference, but the difference will be very small at different times. Okay, so number of molecules are almost the same. So if in a given chamber, at a time number of molecules are not changing significantly, so their average defect will give us a single value of the property. Okay, so whether I measure, if in this room the number of molecules are very large, whether I measure the pressure on this wall or this wall or that wall, everywhere I will get the same value of the pressure. Okay, so that is something which is called as the approach of continuum. So for most of the engineering applications, we will be finding that the number of molecules present in our system will be extremely large, so that we will not be able to feel the void spaces present between the molecules. Okay, and the area of observation which we are considering, at different times in that area almost the number of molecules will remain the same, so that total overall property what we are looking, that is almost same material. Okay, so that is something which is called as the approach of continuum, and it helps us lot in analyzing the engineering systems, because if for everything you have to look into the molecular motions, then you cannot even complete the computations. Okay, so say if you have to solve the equation of motion for 10 to power 40 molecules, even your advanced developed computers cannot solve it within the reasonable time scale. Okay, so it may happen that you started analyzing the molecular behavior for this room at this stage, and maybe when you are getting 80 years or 100 years old, by that time you will get the solution. So we don't have that much time. Okay, so that is where actually continuum helps us. So here one typical non-dimensional parameter is there, which is useful in deciding whether the approximation of continuum is justified or not. Okay, so that particular parameter is called as Knudsen number. Okay, so Knudsen number is typically called as, is given as Kn equal to lambda by L, where lambda is nothing but the molecular mean free path and L is characteristic dimension of the system under consideration. Okay, so whatever the system which we want to analyze, so what is the characteristic dimension of the that is something which is given by L. Okay, so for example, if you talk about this room, so this room is, I can consider that kind of if this whole room I want to analyze, so this is a rectangular shape, and if just I consider its one of dimension, so length of its one dimension is about 5 meter, so 5 meter is my characteristic length. On the other hand, if I talk about the mean free path, molecular mean free path, so molecular mean free path for air at atmospheric pressure can be of the order of 10 to power minus 8 or 10 to power minus 9 meters. So what is molecular mean free path? The distance traveled by molecules between the successive collisions. Okay, so that will be of the order of, because so densely packed molecules we have at atmospheric pressure, the number of molecules is huge, so they will be taking a distance of about 10 to power minus 8 or minus 9 meters, exact number you can refer from the textbook, at atmospheric pressure condition between their successive collisions. Okay, so you can see the Knudsen number for this room will be very, very small. Okay, so there is a definite number. When Knudsen number is less than 0.01, then we can say that that system can be perfectly analyzed by considering the approach of continuum. If Knudsen number is in the range of 0.01 to 0.1, then we call that as slip flow. Okay, so presently, as I told you, whenever we are talking about the fluid, we are saying that if it is interacting with the adjacent boundary, it is taking the velocity of that adjacent boundary. So that is called as no slip condition. But if your Knudsen number is in the range of 0.01 to 0.1, then that no slip condition is not actually applicable, and we have to go for the slip flow models. When Knudsen number is in the range of 0.1 to 10, then we call transition flow. So transition flow means where the transition takes place from continuum approach to molecular approach. And if Knudsen number is greater than 10, then we have to consider the molecular flow. Okay. You can do a small exercise. Consider that you have a cube of size 1 centimeter by 1 centimeter by 1 centimeter. Okay, and try to find out the number of molecules that volume will be having. So take this as an exercise. So you can simply consider that 22.4 liters of any gas is equal to Avogadro's number. Okay, that will be giving you 6.023 into 10 to power 23 number of molecules. So now you can correspondingly find the volume of 1 centimeter cube and then find out the number of molecules that will be having. So that will be also having number of molecules about 10 to power 28 or 29. So you can see that much large number of molecules. You can imagine 1 centimeter distance is something like this. So 1 centimeter by 1 centimeter by 1 centimeter cube, that is having so many large number of molecules. Okay, you can calculate it. Okay. So that is the reason that for majority of the things which we will be dealing in this subject, our sizes are not less than, say, in engineering application, less than millimeters or micrometers. Very rare some application, particularly for biofluidics, etc., you can find where if you are talking about the flow of blood inside the blood vessels, there you may have, say, micron size. Otherwise, for most engineering application, it will not be less than the millimetric size. And in a millimetric size, the number of molecules present in the system will be so high that the approach of continuum can be well justified. Okay, is this one clear? Okay, now next comes, what is our interest in fluid mechanics? Typically, in fluid mechanics, we will be having a situation where flow of the fluid is happening. So first primary thing is that we wanted to know the parameters of the flow field. Okay, so our first interest is that what is the value of velocity vector at different locations and how it is changing with time. That is something which we want to know. Okay, along with this velocity field, there will be of course changes in other parameters as well. Okay, so if when you will be studying the different properties which are associated with your thermodynamic conditions with a pure substance, okay, so you will be finding a number of properties. So let me number some 3 primary properties which are very essential. These are nothing but pressure, temperature and density. If you have any fluid, always we want to know, we talk about, even in our common day-to-day understanding also, we typically refer these properties. So pressure, temperature and density. So these are considered as kind of primary properties. And these are also easy to measure as well. If you want to measure pressure, if you want to measure temperature, you have the devices available. Okay. Then comes another set of properties which typically are needed when we are considering the fluid, and if we have to see that what are the changes which are taking place in the fluid under different conditions. Okay, so these properties are, first is given by symbol U, that is called as internal energy. Then another important property is which is called as enthalpy. Then after enthalpy, can you tell me? Entropy. Then specific heats. So these are typically the other important properties which I can say kind of secondary properties. Okay, so if I know any of the primary properties, then I can relate these secondary properties. Okay, then after this there is one more state where we have some transport properties. So one of the properties is given by symbol mu, which is called as dynamic viscosity, and this is another property we have is given by symbol K, which is called as thermal conductivity. So these are nothing but the transport properties. So whenever I am talking about the fluid flow will always be there. So flow is the primary thing. So it means velocity has to be determined whenever we are talking about the flow. But along with the velocity, which properties, the other properties which can change during the flow are pressure, temperature, density. Then these are primary properties. Then secondary properties like internal energy, enthalpy, entropy, CPCV. Then there are some transport properties mu and K. Okay, so all these properties are actually relevant in understanding the different processes which are happening in engineering in nature, which are resulting in changes of the fluid behaviors. Okay, so in this particular course of fluid mechanics, our major interest will be on viscosity. We are not much interested in thermal conductivity. That is the part of heat transfer which you will be studying in the next year. And then CPCV also to some extent we may find the use, but not much, because we are not dealing with any aspect where substance is undergoing through the heat transfer effects. Okay. So our major interest will be in these parameters and this parameter. And typically whenever we will be talking about temperature also we will be almost considering the isothermal condition. So at atmospheric pressure, at atmospheric temperature only we will try to analyze the different fluid flow situations. So we will not be having the variation of temperature, particularly in this course of fluid mechanics. Okay. So now when we have a substance, if I have to determine its properties, so in thermodynamics there is something which is called as state postulates. So as per the state postulates, if I know any two independent properties of a simply compressible substance, then I can determine all other remaining properties. Okay. So for any simply compressible substance, you must have two properties known. If two properties are known, then you can relate all other relevant properties of that particular substance from the set of only two properties. So there are certain set of equations which relates that, and typically there are property tables are also given in most of the textbooks, from where if we know two properties then we can determine other properties. And majority of the time for fluids, pressure and temperature are so if I have to determine any property, I will be just making it a function of temperature and pressure. So pressure and temperature are the typically primary properties which can be easily measured, and by just knowing these two properties I can determine the value of all other properties. Okay, so this is the reason whenever we discuss any other property, what we first analyze? We first analyze how these are connected to pressure and temperature. Okay, for example, when I will be defining viscosity, we will see that how viscosity varies if we vary the pressure, how viscosity varies when we vary the temperature. So same is applicable for all other properties. Okay, so typically pressure and temperature are the very common properties which can be easily measured, and by just knowing these we can determine all other properties. Okay, so that is something which comes from the fundamental understanding. Now what is a property? Can you define what is a property? We have named many. Exhibited by the substance. But what does it do? A property is something which characterizes the unique thermodynamic state of a substance. Okay. So for example, if you have water at 1 atmospheric pressure and 25 degrees Celsius, it is one unique state. Corresponding to this, you will be having different values of internal energy, enthalpy, entropy. If you take the same water at 1 atmospheric pressure and 120 degrees Celsius, it will be in the vapor phase. It will be having different values of internal energy, enthalpy, and entropy. Okay, so property is nothing but a characteristic of the representation of unique thermodynamic state of a substance. Okay, so maybe in your thermodynamics course you will study it in more deeper details, where properties are classified as extensive and intensive properties. So extensive are those which depends upon the quantity of the matter, and intensive are those which are independent of the quantity of the matter. Okay, so now we will stop, and maybe, so if you have any questions that we can take up now.